So let's take a look at this generalization for when we can take the derivative of an integral, specifically called the second fundamental theorem of calculus. So let's say we had some integral for some function defined on the bounds of h of x to g of x. So now, instead of using a to b, where a and b were normally numbers, now we can have bounds as functions. For instance, maybe there's a bound of x or an x squared, like you can kind of see at the bottom of the page. Now we're starting to get into variables in those bound locations. So let's say that some function capital F of x is defined as this integral. Well, if I want to take the derivative of capital F, meaning if I want to put a prime mark on this side, we have to think about what's going to happen to the right side. And if you really think about how the connection between integrals and derivatives are related to each other, it kind of makes sense that an integral is initially telling us to work backwards, aka find an antiderivative. But if you were to then take a derivative of that antiderivative, you would be back to what you started with. So that's why we kind of saw a pattern in the first few examples on the last page, why our derivative result was the same as the original integral function that we started with. What happened though was, depending on what the bounds were, we didn't always end up getting the same exact function back. So this is why the bounds are pretty important. When we're using the second fundamental theorem of calculus, aka when we're taking the derivative of an integral, you do not have to find an antiderivative. Okay, I'm going to repeat myself. You do not have to find an antiderivative. You do not have to work backwards. We're simply going to be using some knowledge, okay, and understanding that if we were to work backwards and then take a derivative, we're going to be back to where we started with this little f of t function. So that's what we have here, and that's what we have here. But notice how we're going to take this top bound of g of x and plug it into this function. Okay, that's what this notation is telling us to do. Take g of x and plug it into f. But since g of x is a function, we're eventually going to have to multiply by the derivative of that bound. Okay, something very similar to the chain rule. Again, we're taking the derivative of an integral, so we should technically consider the derivative of the bounds as well, now that they're functions. So we're going to plug in the top bound times the derivative of the top bound, and then we're going to subtract, plugging in the bottom bound, which we see here, times the derivative of the bottom bound. So it's very similar to the first fundamental theorem of calculus, where we do that top minus bottom idea, but we do not have to work backwards. We're simply plugging in the top bound, but we do have to consider, again, the derivative of the top bound, and that's what we're going to multiply by. So this is only for taking the derivative of an integral. Okay, second fundamental theorem of calculus. So we're going to revisit these examples that we did on the previous page, and I wrote down the derivative results that we got. We're going to try to see if we can apply this second fundamental theorem of calculus to get the same result. Because notice how, in order for us to get these results, we first had to work backwards and then take a derivative. Instead of having to do kind of that two-step process, we're going to see if we can get straight here by using this theorem. So if we're going to take the derivative of this side, which would be f prime, we then have to take the derivative of the right side. And notice how that would involve taking the derivative of an integral. So we're going to use the second fundamental theorem of calculus to help us do that. It simply states that we're going to take the top bound and plug it in for the t's. So this would be 4x minus x squared. We then have to multiply by the derivative of the top bound, which would be 1. Next, we're going to subtract, plugging in the bottom bound, so that would be 4 minus 1. And we have to end it off by multiplying by the derivative of the bottom bound. The derivative of 1 would be 0. So conveniently, this multiplication of 0 is going to go away, and this quantity times 1 is just going to remain itself. So notice how it matches the same result that we did kind of the long way on the last page, where we had to first of all work backwards and then take a derivative. This second fundamental theorem of calculus is going to be drastically important for us for functions that we cannot easily work backwards from. For instance, if I wanted to do an integral of 1, or maybe I'll change this to 2 to x of e to the sine tangent of x, for instance. All right, let's say capital F of x was defined as this function, and I wanted to take the derivative of f prime, which means I'd have to take the derivative of this integral. I do not want to physically find the antiderivative for this function. Okay, that would be very difficult to do. So that's why instead of having to work backwards and then take the derivative, we can use this second fundamental theorem shortcut, if you will, which involves plugging in the top bound times the derivative of the top bound, and then minus plugging in the bottom bound times the derivative of the bottom bound. So in essence, the second fundamental theorem is a shortcut for us. All right, let's try the next one. So if I want to take the derivative of the left side, I have to take the derivative of the right side. So the derivative of an integral, hopefully that light bulb goes off, meaning second fundamental theorem of calculus. I'm going to plug in the top bound times the derivative of the top bound minus plugging in the bottom bound times the derivative of the bottom bound. Again, we're multiplying by 0, so that's just going to go away, and cosine of x times 1 is just going to be cosine of x. Again, matches what we got previously when we did it the long way. Okay, without utilizing the second fundamental theorem of calculus. So those were the first two examples where our ending derivative result matched kind of the original function that we had in the integral, just with an x instead of a t. These last two examples were the ones that did not match exactly. So let's see if the second fundamental theorem of calculus can compensate for that difference. So in this case, if I want to take the derivative of the left, I'm going to have to take the derivative of the right side. So that would involve taking the derivative of an integral. So I'm going to plug in the top bound first times the derivative of the top bound minus plugging in the bottom bound times the derivative of the bottom bound. So 1 times 0 is going to go away. Over here, power to a power would be x to the 6th. And I still have to multiply that by the derivative of the top bound, which is 2x. So in the end, I get 2x to the 7th. And notice how that matches what we had when we did it the long way. So it seems like the second fundamental theorem of calculus compensates for that difference that we have since we changed what the bound was. All right, let's try the other one just for good measure. If we do the derivative of the left, we're going to do the derivative of the right. The derivative of an integral means second fundamental theorem of calculus. So I'm going to plug in the top bound times the derivative of the top bound minus plugging in the bottom bound times the derivative of the bottom bound. Times 0 is going to go away, and simplifying this side, the square root of x squared is just going to be x. I still have to multiply by the derivative of the top bound, which was 2x, so I'll get 12x squared. Again, notice how it matches. Okay, so just to reiterate, the second fundamental theorem of calculus is when you are taking the derivative of an integral. Okay, second fundamental theorem of calculus involves taking the derivative of an integral, or at least looking for that concept in a question or in a problem. So we're going to plug in the top bound times the derivative of the top bound minus plugging in the bottom bound times the derivative of the bottom bound.